Hi, John Valvano here. In this video, we're going to talk about style, requirements, specifications, and constraints. Now, one of the beautiful things about software is how we name things, how we name our variables, and how we name our functions. Now, when you define a variable or a function, what it is usually perfectly clear at that spot, but good name will convey that same clarity also to the places where the object's used. In other words, if I can look at a function when it's invoked and know what that function does, it's a good name. That name should be clear. It shouldn't be ambiguous. It should give hints about the type. In other words, is the variable a pointer? Is it a integer? Is it signed? Is it unsigned? We're going to use the same syntax, the same structure of naming throughout our entire project. Now, I'm going to use a combination of prefix, upper lowercase, capitalization, and underlines in order to identify or clarify what that is. For example, when I use a constant, I'm going to use all uppercase. And if I need to have multiple words, I'll use underline. These are pound defines. These are things that never change during execution. And then if I have a local variable, I'll use the no underlines, and the first letter is going to be lowercase. Whereas global variables, the first letter is uppercase. Next, to decide whether it's private or public, I'm going to use the underline. So variables without an underline are private, either to that function, to that file. They are not accessible outside the module. Whereas when I use a underline, those objects are accessible throughout the entire project. Now, public global variables are probably bad style, but if you wanted it, this is what they'd look like. And when I have a public function with the underline, the thing in front of the underline is going to tell me the module. Okay, this is a timer module, a timer function, a FIFO function, a keyboard function. And then again, I'm going to use the names to clarify what it is. So everybody knows what last character typed is. That's the last character typed. Okay? Again, good names convey what they are, what they mean, beyond where they're defined. Okay? Then comments, we're going to see really two types of comments in the code file, which is written by you for yourself, for your coworkers. We're going to describe how it works. Why did I do it? How did I make decisions? What hardware do I need? In here is how it's implemented. Okay. As opposed to the header file, we're going to describe what it does. So this separation of concern in the code file is how it works, and in the header file is what it does. And this allows us to remove the complexity for our users. Now, the reader of the header files are the ones who have purchased our software or are going to use our software. This is the interface. These are the prototypes for the public function. And the comments in here are going to assist us in using the functions. Okay. One of the cool things we do with header files is actually use them to create documentation. So Doxygen is one of many automatic documentation systems. And so here's a typical header file information, and down here is a prototype. SSD 1306 drawstring. Again, it's a public function because it has the underline, and it belongs to the module SSD 1306. And embedded in the header file is what it does. Now, if you use this fancy Doxygen syntax, what you can do is invoke Doxygen on your entire software system. It'll parse all your header files and then create a document which is links, it's got pictures, it's got, here's an example. That particular header file looks like this in the documentation. So again, the key question here is, if this is all you had to know about drawstring, could you use it? Could you call it? Could you figure out what the 4 functions are and write code that invokes this function? Right? And that's the beauty of the header file, is it separates separation of concern. It reduces the complexity of your software so that your user only needs to know what it does, and the abstraction, it doesn't need to know how it works. All right. So as I said earlier, good software doesn't require any comments. Well, that's a little bit of an overstatement. In the code file, we're going to put in how it works. Because we might change it, you could put in why you did it. What else could you have done? And because you know your software is going to be changed, you could put in how to change it. Okay. Software needs to be tested, so you can put in how we're going to test it. Okay, so again, you're going to leave comments for yourself, and your coworkers in the code file understands how it works. And you don't need stupid comments that tells me that n+1 is n+1. Okay. All right. Next, let's look at the requirements document. Now, the requirements document is an unambiguous, high-level requirements design. Okay, so this is where we start. This is where you communicate with your customer about what it is you propose to do. This is an interactive document between you and your customer, to the point at which once you agree on this, money exchanges hands, you build software, and in here's an unambiguous description of when you're done. Okay? And so without a requirements document, you can never finish a project. Because if you don't write down what the expectations are, you and your customer are not going to see eye to eye, and the customer's not going to like you. Okay? So there are lots of formats here. This is one of the simpler ones that's been redacted even more, and I'll show it to you what it is specifically for your Lab 3. Again, it's meant to be unambiguous, but very high level. Okay? The first part is, and what are we doing? How will it be developed? Who does what? How does it interact with things we've done in the past? Because engineering requires a lot of terminology, and sometimes that terminology is not agreed upon. Whenever we use an engineering term, we're going to define it in our requirements document, just so that everybody knows what a critical section means, or everybody knows what latency is. If you've got intellectual property, how are you going to manage it? Okay, so that's the introduction part. In the function part is what it does. You know, it's a clock. You know, it's got hours and minutes. It's got output in numbers. You know, it makes sounds when the alarm goes off. It's got buttons to allow you to set the alarm. You know, notice it's very high level. Okay, it will allow the operator to set the alarm. Okay, it doesn't tell me exactly which button does what. That's a lower level document. This is the high level. Okay, how will it be developed? What are the intermediate stages? What kinds of prototypes are going to be developed? How we're going to evaluate its performance, both qualitative and quantitative. How will it use? What are the minimum requirements for the inputs? What are the minimum requirements for the output? And how are we going to make sure it's safe? And then at the end, this is what we're going to deliver to the customer: reports, circuit diagrams, software, etc. So again, a system development without a requirements document can never be finished, because it's in this document that you and your customer, or in our case, you and your teaching assistant, agree on what it is you're going to do. So how do engineers design? Well, they write a requirements document and they build stuff. Okay, that satisfies the requirement. Okay, make sure you understand the problem. Ask lots of questions until you understand the problem. Figure out what rabbit hole you're going to go down and what rabbit hole you're not going to go down. Okay. One of the fun things you can do in this class is develop your own style. Practice with it. You're going to be boss one day. Okay. You're going to impose a style on your coworkers. Okay. So why don't you have fun with it? Some of the performance measures we'll see in this class is bandwidth, which is either number of calculations performed per second or the number of data bytes transferred per second. We've been talking a lot about latency and response time associated with real-time systems. Other efficiencies are how much RAM do you need, how much ROM do you need, how accurate does it have to be, the difference between truth and measure. The smallest change that can be detected is resolution. The amount of noise is if I have a constant input and I repeat it over and over again. What is the variability of those multiple observations? You saw that in lab 2. Okay? The central limit theorem allowed us to reduce the standard deviations. Okay? Now, if we have the same operator, the same conditions, the same day, the same machine, and do it over and over again, we call it repeatability. If we have different operators, different days, different machines, whatever, we're going to use that variability as reproducibility. Okay? Engineers always are lived in constraints. It's actually a feature. You only got 32 kilobytes of RAM. It forces you to make decisions. But you'll see that when we do our projects this semester, we'll be interested in how much power, how long will it run on a battery, can I fit it inside the box. Of course, you got to spend a lot less than 100,000 in this class. Okay, and again, constraints in this class are going to be labs are due approximately once a week. Okay, so in summary, practice with this requirements document. Okay, because labs 3, 4, and 5, we're going to write it for you. But labs 7, 8, your project, you're going to have to write your own, okay? Again, you want it to be negotiable, so you got to do it early. You got to agree. Make sure you don't make too many changes, because you'll then, if you never finish the requirements document, you can never finish the project. Okay, so this class is a lot of design, and it's around that requirements document that we're going to approve and negotiate and let our customers know when they're done. Okay, so enjoy.